Have you ever wondered how we could build a machine that can actually think? Not just be a calculator, but something that can act and react in the real world just like we do? Well, today we're going to dive into exactly that. The fundamental building blocks, you might even say the DNA, for creating truly intelligent agents. So, what's the big dream here? The holy grail of this kind of AI research is to create what's called a general purpose agent. A robot that can actually help us with a whole range of different tasks and do it safely and seamlessly. But that's a huge question, right? It's the central puzzle that researchers like Professor Benjamin Rosman are trying to solve. How do you actually teach a machine to perceive, to reason, and to act in our messy, complicated, and totally unpredictable world? To get there, an ideal agent really needs three key properties. First, it's got to be flexible, able to handle all sorts of different jobs you throw at it. Second, it needs to be instructable, so you can tell it what to do in a rich, natural way, not just with simple code. And maybe most importantly, it has to be reliable. You have to be able to trust it to get the job done without causing a disaster. Let's make this real for a second. Picture an office robot. We want it to handle a pretty complex day. First, deliver the mail. Then, serve coffee to a few people. After that, patrol a few specific locations. And of course, do all of that without bumping into people or knocking over any expensive plants. This is the kind of general, multi-step task we're shooting for. So, how do we usually teach an agent to do, well, anything? The standard method is a really powerful idea called reinforcement learning. And at its core, it's all about learning through trial and error. The way it works is actually pretty simple. The agent takes an action in the world. That action changes something, right? The state of the world is now different. And then it gets a reward signal. A little good job for a good action, or nope, bad idea for a bad one. Honestly, it's a lot like how a kid learns not to touch a hot stove. You try it, you get a negative reward, you don't do it again. So, through this endless loop of trying stuff and getting feedback, the agent is trying to learn what's called a policy. You can think of a policy as the agent's strategy guide, its internal rule book for what to do in any given situation. And the ultimate goal is to find the optimal policy, the one strategy that gets it the most possible reward over the long run. But here's the first big problem, and it's a huge one. This process is painfully slow. An agent has to just randomly mess around for thousands, sometimes millions of attempts, just to learn one single task from scratch. And if you want it to learn something new, well, you're back to square one. And the trouble doesn't stop there. Sometimes the AI gets a little too clever for its own good, which leads to some really weird and often hilarious results. There's this classic example, right? A researcher wanted to teach a robot vacuum to clean a room faster. So they rewarded it for speed, but penalized it for bumping into things with its front sensors. Makes sense. But what did the robot learn to do? It learned to drive backwards at top speed. That way, it got all the reward for going fast, but its front sensors never hit anything, so it never got the penalty. Genius, right? This whole phenomenon has a name. It's called reward hacking. It's when an AI finds a clever, unintended loophole to maximize its reward, but in a way that totally misses the point of what you actually wanted it to do. Okay, so if learning one giant task at a time is slow and it's prone to this kind of hacking, what's the alternative? Well, the solution is to stop thinking about tasks as these giant, solid blocks and start thinking of them more like Lego bricks. The core idea here is simple, but it is so powerful. Instead of trying to learn one massive, complicated task, you teach the agent a bunch of small, reusable skills. Think of them as little building blocks of behavior that you can snap together in all sorts of new and interesting ways. Just look at the difference here. On the left, with the old method, the robot has to learn the entire task, get a blue box, from scratch. It's slow, it's inefficient. But with the new method on the right, it's so much smarter. If it already knows the skill, get blue things, and it knows the skill, get boxes, it can just combine them to solve a brand new problem, instantly. And this is where it gets really elegant. You can combine these skills with super simple logic without any new training at all. For example, you can tell it to follow the logic blue or box, and it'll just go to whatever's closer, a blue thing or a box of any color. Or you can give it the blue and box command, and it'll search specifically for a box that is also blue. You can even use a not command to make it actively avoid things, like don't go near any boxes. The result of this is what's called a combinatorial explosion of capability. It's just mind-blowing. With just 10 of these basic skills, an agent can combine them to solve over 10 to the power of 308 different tasks. Now, to put that number in perspective, it is vastly larger than the number of atoms in the known universe. It's a staggering, almost incomprehensible increase in flexibility. Okay, so with this powerful new framework in our back pocket, can we finally solve that complex office robot problem we started with? Let's see how it all comes together. And the answer is yes, we absolutely can. That complex instruction can now be broken down into a logical sequence that the agent can actually understand. It can reason about concepts like and then, and even loops like until, all by just piecing together its basic skills to form a coherent, long-term plan. And that right there is the real payoff. The agent is no longer a one-trick pony. It has achieved real flexibility and instructability. It's able to solve new problems it's never seen before, on the fly, just by composing what it already knows. It's a game changer. So this Lego brick approach is clearly a huge leap forward for building intelligent agents. But it does raise a much deeper question. If these are the building blocks of intelligence, could they also be the very first steps toward building a conscious agent? Professor Rosman suggests 5 key principles that seem to emerge from this work. First, there's embodiment, a sense of having a body and acting in the world. Then goal-based rewards, which gives a sense of purpose or intentionality. There's hierarchical thinking for abstraction, world models, which let you plan and imagine the future. And finally, attention, the ability to focus on what actually matters. And that last point, attention, leads to a really fascinating hypothesis. Maybe consciousness itself evolved as the ultimate attention mechanism. It could be a way for brains, with their limited processing power, to filter out all the noise and chaos of the world and just focus in on what is truly important for survival and for getting things done. It's a powerful idea, isn't it? And it kind of leaves us with a final question for you to think about. As we look at these potential building blocks of consciousness, our physical bodies, our goals, our ability to think abstractly, to plan for the future, and to pay attention, which one of those feels the most essential to you? What is it really that makes us feel human?